The process should appear entirely familiar to those who work with random graphs and hypergraphs. It is exactly the same procedure used to find the 2 core of a random hypergraph. Anybody know what a hypergraph is? Bueller? Yeah, me either. Today we're talking about invertible Bloom filters, or invertible Bloom lookup tables as it's called in the paper. I think invertible Bloom filters is just a more succinct way of describing it. Maybe that's not totally accurate, but meh. This is part 2 of a 3-part series, I guess, that is getting us up to a new set reconciliation algorithm that I really want to talk about. To get there, we need to first start with Bloom filters. That was the video before. This is the middle video where we're going to talk about invertible Bloom filters, and then we'll get to the fun, juicy bits. This paper is lovely, interesting, exciting. There's some cool stuff. There's also this like womp womp moment at the end that we'll get to. Let's start where we left off. Where we left off was with Bloom filters. A Bloom filter is a compact bit representation of a set. You take the elements of a set, you hash them, you stick them into this bit field, and it'll probabilistically tell you whether or not some new thing is a member of that set using that bit field to check against it. Probabilistically, because depending on how big the Bloom filter is, you can lose or gain some information. If you want more details, check out the Bloom filter video. We're now going to move on to an invertible Bloom filter. So just to compare the two, let's compare the operations that we can get. A Bloom filter gives us insert something into the filter from the set and check. That's it. You can't remove anything, you can't do anything else. An invertible Bloom filter is going to support new operations. And those new operations are insert, okay, put something in, but now the thing that we're going to put in is not just a value, it is actually a key value pair. And we'll get to that in a second. It also supports deleting stuff, so we can pull things out of the filter. That's actually quite relevant. And what gives us some of the other properties. We can get a value for its key. So we can treat it basically like a hash map structure or a dictionary structure, if you want to refer to it that way. The one that is kind of the magical, very interesting one is list. You can use a invertible Bloom filter or an IBLT, I'll acronymize it to get all of the elements inside of the filter, which is a very, very, very interesting property. And most of the time we'll spend today, we'll be talking about how you actually go about listing those elements. Everything else is kind of a derivative of that. So just to sort of give you an orientation, I have laid out this terrifying looking thing to explain how an invertible Bloom filter functions under the hood. And so what we're seeing here are, now we've moved from Bloom filter where every bit represented a cell or represented a place where we were going to put data, to now we have a larger, sort of much more logical structure looking thing that will actually take up multiple bits in the representation of the filter, but its representation as a data structure we'll call a cell. And so a cell, in this case, contains 3 things, every cell does. And the width of the filter, the M value from a Bloom filter representation, is the number of cells, not the number of bits in the Bloom filter. And so in this case, for a invertible Bloom filter, you have to pick a fixed size for your keys and your values, which in this case, for this example, I've chosen 4 bits for both the key and the value. And so there are 3 things in every cell. You're going to have a key sum, a val sum, and a count. The things we're going to be putting into this Bloom filter today are going to be integers. But as you can see along the bottom, we have these bits representing keys and values. And the authors of the paper make the point that there's actually no loss in generality in representing this with numbers. You can use this to represent strings, you can use this to represent anything that is the same length in terms of bytes that it is stored in memory with, because it's just bytes. And you'll see as we go through this that the techniques used to manipulate those bytes are compatible with largely any data structure. And so getting back to the description, I've color-coded some of these just to make it a little easier to understand. So you can see below each cell its actual byte representation or bit representation. And so each cell, because we've chosen 4 bits for keys, values, and sums, we have 12 bits per cell. And so if you look at this whole thing, this is going to be 12 times 8, which actually works out to a multiple of 8, which is great, but that's not totally relevant for our toy invertible Bloom filter. Right now, the whole filter is uninitialized or is initialized with all zeros. There's nothing in the filter, it's empty. And so by adding something, we're going to take a value. And what just happened there is we took that value, we ran it through our chosen predetermined set of hash functions. For this example, we're using 3 hash functions on a M value or a bit invertible Bloom filter with 8 cells. M is the constant you'll see in the paper. And so now this invertible Bloom filter has a key and a value pair of key 1, value 2. And so what we did is we took the key and we hashed it across 3 different hash functions, and that ended up in 3 distinct cells. If the cells overlap, it's always a distinct addition. And so every time we go to add something, we set the key to the sum of whatever the key is for that cell, the value to the sum of whatever the value is, and the count we always increment by 1 because we added 1 thing. And so now we have 3 elements in our IBF, Invertible Bloom filter. Let's use that acronym. In our IBF now populated with a thing. Let's add another thing. Cool. So now we're going to put key 2, value 3 in this. And again, this is going to modify a few things, and a few of those cells did overlap that time. And so now we have a count of 2 for some cells and a count of 1 for a couple of these adjacent cells. Keep going. Let's add 7, 0 combination. So 7 and 0 populate a different part of the filter. This is again a property of the hash function that you're using. It should ideally, and really kind of needs to distribute everything evenly across the filter. And now we have 3 values inside of our Bloom filter. Let's add 1 more for good measure. And now we have what will be our sort of toy, fully hydrated invertible Bloom filter. And so from this point, I'm going to skip how you can actually get a value out of this thing and go straight to reversing the Bloom filter and recovering everything out of it. And so this is the representation of the list operation from the paper. And this is the kind of the whole magic. The idea here is that what we've done is we've jammed 4 key value pairs into this thing. A bunch of them are overlapping. And there exists a technique for peeling all of those values back out and recovering the representation of the key value list using just the bytes. And the reason that that's possible is actually the way that we've been adding a bunch of things to this filter in the first place. We've been using the XOR binary operator to add stuff. And if you've watched any of the Kademlia videos from earlier on this channel, you'll recognize XOR as both my single favorite operator and the one that is the most magical for these distributed systems things. The reason that XOR is magical is because it's a commutative operation. The order is independent. It doesn't matter if you XOR A then B or B then A. And because of that, we can go in and out of the filter. But to do that, we need a starting point, a place where we can anchor the whole conversation of inverting the filter. And for that, the paper refers to a pure cell. A pure cell is some cell within the filter that has a count of 1. And if you think about this intuitively, a count of 1 means there's only one thing in this cell, which means whatever is the key and the value is actually just a key and a value. And so in this case, cell 0 has a key sum of 7, so its value is 7, and a val sum of 0, and its count is 1. And as we can see up here, there is actually a key value pair of 7, key value 0 in our set of things that we added. And so what we can do is, because we used XOR to add everything, we now have a destructive operation for removing that same thing. It is worth noting that listing the elements in the filter destroys the filter. And so the paper says, hey, if you want to, list everything out, you need to make a copy of that. It's just kind of like not great if you're doing it locally, but interestingly enough, if you were to use this to reconcile data over the wire, you're going to get a copy in the form that you're going to have to send that to the other node. And so it's not really a problem for this use case. But just to show the recovery process, we'll now go through and recover everything from the cell. First, we'll recover this key 07. And what that'll do is, again, take those hash functions and just peel out everything that matches that hash function. And what that'll do is decrement the filter one more time. And so now, in the process of removing that first value, we recovered key 7, value 0. We have uncovered more pure cells. And this is called peeling. And what we're doing is opening up and peeling the filter to extract values one at a time. There is a probabilistic relationship between how likely this is to be doable, and it has to do with how many elements you've added to the filter and how big the filter is. And that's one of the most important characteristics of an invertible Bloom filter that is really important to keep track of. You have to, above a certain threshold, this entire system doesn't work. If you don't have a pure cell to work with, if you've jammed too many values into the filter, the whole thing won't give you anything back. You will fail to be able to list any elements in it, which sounds super gnarly. It kind of is. Probability and probabilistic data structures are funky. Whatever. Anyways, let's keep going. And so next we can recover from cell 1. We've encountered a pure cell there. And so we can again peel that out, recover key 1, value 2. Again, keep going. We pull this out. And again, this is happening by taking the pure cell, running that through the predetermined set of hash functions, and using the results of those hash functions to XOR the values out and decrement the count by 1. That's how we're getting each of these values. Doing the last value, we can now show that we have actually managed to return this Bloom filter back to its empty state and extracted all of the values out of it. Interestingly enough, the paper says and points out that in a lot of situations, you won't actually get back to just straight zeros. The definition of when you have extracted everything you can from the filter is when you have no remaining pure cells. And we'll see some more about that in a minute. But just to compare these, the values that we added and the values that we recovered are the same set. They came back in a different order, which is kind of fun and interesting, right? That's a property that's being shuffled by the virtue of the way that things are being added to the filter. But I think that's kind of mind-blowing, right? Like, if you think about what just happened, we took a whole bunch of information, compressed it into this filter, potentially moved it over the wire, and sent it in this very compact, highly overlapping representation of this data. And then we were able to peel and reopen that thing. It's a form of lossy probabilistic compression that is just kind of total magic. What does this have to do with set reconciliation? The thing that is really interesting about this is the representation of this is just bits, and you've used the XOR operation to add everything to it. So now we can actually take two invertible Bloom filters and XOR them together. And what you get out the other side is actually the difference of the sets that they represent. I'll say that one more time. If you XOR two Bloom filters together that represent slightly different sets, you'll obviously know if they're equivalent because they will be literally byte for byte the same thing. But if they're slightly different, XORing them yields the difference in the sets. And as long as that difference is small enough that you can invert it, what you will get are the sets, the elements that are missing from one of the filters. And so here, let's do it. We've got two Bloom filters here, invertible Bloom filters, pardon me, A and B. And first thing we're gonna do is hydrate them with some stuff. And so we're gonna add stuff to A, we're gonna add 3 values to A, 4 values to A, and 3 values to B. And this is what that looks like just as their bit representations. Again, we're using the same structures. What we'll do now is XOR them together. So take A, B, XOR it up. And here's what that's gonna look like. We'll take all of these cells and all of these representations, go through, and what we're doing is taking each, basically thinking about this in a line, and anywhere where you see difference, that is what the XOR operation is gonna highlight. And so we'll see here, we have a 0 and a 1, and what ends up at the bottom is a 1. And so the resulting XOR invertible Bloom filter between the two is now only has cells 3, 4, and 5 populated. And you can see here that the counts for cell 3, 4, and 5 are 1, 3, and 1 respectively. And so if we look up here, we can see intuitively, because we have a chart, that key 3, value 9 is missing from set B. And so XORing these two together, you would, in practice, know which side you are. So you would know if you are A or B, and you would be able to use that to infer what this difference means for you, whether you are missing something or need to add something. But in this case, we can go through and say, cool, I now perform the same process that I performed before to invert the Bloom filter and get the list out. And here we have 2 pure cells and one with a value of 3. And so let's invert the cell, or pardon me, invert the Bloom filter. And what we recover from it is key 3, value 9. Isn't that ridiculous? Like, it blows my mind that you can take these just like seemingly random sets of bytes, run them through this XOR operator, and what comes out the other side is a structured description of the value that you're missing. That is mind-blowing to me. And I hope you find it as mind-blowing as I do. What is not so mind-blowing to me is this is a probabilistic data structure. And so you can kind of see that here, even in this toy example, there is a remaining cell that has no key and values in it, but a count of 2. And as it turns out, this is a property of these things. It's possible to just end up with these kind of like errata left over. The software engineer, software carpenter in me is driven to tears by this. It is so frustrating that the thing doesn't return to just 0. But them's the breaks. I will take it if it means that I get this incredible structure that allows me to just take 2 compact representations of sets, smash them together, and get the definition of what both sides are missing. That's amazing. Sadly, there's a catch. In order for this to work, you need to be able to invert the filter, which means you need a pure cell. To get a pure cell with a count of 1, the Bloom filter needs to be big enough such that the difference between the sets yields an invertible Bloom filter, quite literally a Bloom filter that contains a pure cell. Which means to do this exchange and to have it function where you XOR the 2 together and get a good result that is usable, you have to kind of know in advance how big the delta between the 2 sets will be. So if you can imagine a situation where node A and node B are connected by a network connection, and node A has 1,000,000 messages and node B has 0, the difference is going to be 1,000,000. And when you go to invert it, there's a very real chance that that difference will be so large that you can't invert the filter. Or you would have to figure some mechanism out for signaling beforehand what the difference is between the 2. And you can see how there's a bit of an irreducibility here, right? And it kind of takes this whole technique and deflates it really quickly, because any use of this in the wild to date has required both ends to figure out, well, how many messages do you have? How many messages do you have? What do we think the guess is of the difference between our 2 sets? Which basically means you need to know the difference before you try to calculate the difference, which is kind of frustrating, right? And it really sort of impedes the usefulness of this technique. Or does it? And that gets us to the doorstep of this exciting new paper around set reconciliation. That said, the magic and sort of dark voodoo of invertible Bloom filters themselves is just so neat and enticing to think about. And I thought it was a really fun technique to sort of use as a primer for that paper and as an independent bit. In the meantime, I would love to know what a hypergraph is. It's really outside of my realm of expertise. And so I'm gonna spend some time Googling those and see what that's all about. Hope you had fun. Hope you enjoyed learning about invertible Bloom filters. They're delightful. And if you have any questions, comments, concerns, comments below, I guess, sure. Anyways, thanks so much for watching and have a lovely day.